do all that. After a while, you want to do just research and not worry about. Okay. So homework went smoothly, I suppose. Yeah, you had a question also about it. I never got to answering that. So any comments or anything about the course as of now? So I think we're just beginning as it, even though the third week, right? Third week, right? Beginning. Aryan and Abdullah, how is it going? You have a feel for you got settled down in other courses?
Yeah,
kind of. Okay, kind of. Yeah. Have these three been helpful?
Yeah, very.
Oh, okay.
Classes, quantum mechanics.
Oh, that's the first course that's mechanics. Yeah. Yes. Dr. Bird is challenging, but I think I wouldn't say he's challenging. I think I am less challenging, or others probably are less challenging. Yeah. So, yeah. So he do well in that those courses. Yeah.
He's probably the most challenging professor I've had. I've had quite a few graduate courses.
Okay. Okay. Fair. I feel I'm a little. I think this was in the first couple of semesters. I even had a complaint about this that I'm a little forgiving, like I'm lenient with grading. So I think in the first year of the department, there was an official complaint about it. And like not at the graduate level, at the undergraduate level, that could be challenging, especially if there are two people teaching and one is the hardest, one is easy. So it's not the best thing to have. So, okay. Yeah, we barely began on an example. Yeah, maybe I should have a homework, right? Yeah, so homework 2. Let's just nice. Homework 2, I expect will be due next week. So that will be, I think, due February 1, I suppose. This is tentative. By tentative, I mean I haven't posted the homework. When I'm posting it, I'll be more careful about whether I can finish the topics or not. It might be either Tuesday or Thursday. That's best. That's only change that might happen. Okay. So we want to go back, and I want to do one example a little carefully, and that's where I want to switch from a discrete variation to a continuous variation, and we want to introduce the idea of functional derivative for that purpose. I should say sort of a disclaimer here. The method typically used in textbook is slightly different from what I go through here. I personally feel it is a little more rigorous the way I'm doing it, but at the same time, it comes with a little bit more machinery, right? So that's the price you pay. I'm going to teach something. Someone might argue that, oh, you're not prepared for it, but I'll try to go through it slowly and go over it. I personally feel it is useful, but you can use any method in any book. If you're used to this already, that's also perfectly fine. Eventually, the idea is that you have to be able to do variational part of a function. So you should be able to vary a function. So that's the basic idea. Okay, so let's go back and do Snell's law. But this time we did this for one interface, but let's bring in more interfaces. So let's have a situation where we have what is this called? Stratified medium, right? Or layered materials. So this is let's have two, maybe three. In principle, I can keep going. So what are these things? The speed in this medium is decided by what is n0. Like we said, if someone was walking in sand and concrete, is that you walk slower in sand versus concrete. This is speed of light. Speed of light is decided by refractive index. Refractive index is always greater than 1. So it is c over the speed of light in that medium. Let's say this is the 0th medium. This is n1, that's n2, that's n3. And in principle, you can keep going. So in that sense, it's a stratified medium. Medium, discrete also, right? This is basic layered. But of course, one can make this continuous also, right? You could have a material which is changing its refractive index as you move to the right. That is not very common. You don't get materials where you can actually change the refractive index as you go to the right. And it was almost impossible until 20 years. But recently, I don't know how it is made or anything. I think earlier you used to have these glasses which are really thick, correct? But these days you can have really flat glasses. Apparently, you can have materials where you can really control the refractive index very easily. Again, I'm not very sure. So basically, we would like to talk about a situation where things, the refractive index changes gradually from point to point. In a material, it's not easy. Where it is really easy is air. In air, the refractive index just changes because of concentration, number of atoms in a per unit volume, and refractive index changes accordingly. And because of the temperature difference, you can have the concentration difference, and accordingly, you can have refractive index changing. And that's the cause of mirage. We mentioned that last time. And that's one way to look at it. But let's begin with discrete situation. So there's a distance here. So let's have a distance. So this is x. And let's say this is x0, this is x1, this is x2, this is x3, and so on. So it's discrete in that sense. It doesn't even have to be equidistant, but I don't mention anything about that. And let's have a similar situation that one would like to start from one point on the extreme left and reach a point on the extreme right. I seem to be ending here in 3, but in principle, you can go all the way to the right. But for the analysis purposes, let me just pick 3 of them. Now, if I'm going from here to there, an arbitrary path would be, I go anywhere on this, right? I go in a straight line here, I don't even have to go keep going up. I can actually come down if I want any path, like correct any path. It doesn't have to be keep going up and up. So this is x1. So let's say this is x1, y1. This is x2, y2. What are the variables that are free? So this two, I keep these two fixed, and I ask along which 2 points should I connect so that I reach from the lowest left bottom to the top right in the shortest time possible. That's our goal, right? So time taken is equal to, in general, let's say T1 plus T2 plus T3. So it says T1 plus T2 plus T3. I seem to be stopping here, but our analysis in general can be generalized very quickly. So even though I stop at T3, that means that I'm not varying this. Right? T3 is not being varied. Only Y1 and Y2 is being varied. What is this equal to? Since T1, right? So T1 is the distance traveled. So let's say this is S1, right? So yeah, S1, S2, S3. So this is S1, that's S2, that's S3, the distance traveled. So T1 will be equal to S1 over V1, but V1 over C is N1, so that's N1 times S1, and I have to divide by C. The time is refractive index times the distance traveled in that medium divided by the speed of light. Just a physical principle. Multiply by C, so this is C times T will be equal to N1 times S1 plus N2 times S2 plus N3 times S3. And if necessary, if I were to have this also varying, then I keep going to multiple layers. This is an arbitrary path, and if I want to minimize it, I would say that, oh, I want to pick this. This is the only variable possible, right? Y1 and Y2. Rest everything is physically constrained. X0, X1, X2 is all physically constrained. It is Y1 and Y2. This I can change accordingly so that the time is a minimum. I can change my Y1 and Y2, and the question is, what should Y1 and Y2 be so that this time is a minimum? So let's say, let me actually write this as C times T as a function of Y1 and Y2. And let's ask for so for what Y1 and Y2 is T is C times T or T minimum or maximum. In general, we will say extreme. So that's the question we are addressing. So immediately we take the derivative and set it to 0, right? So we would say vary time with respect to Y1, that should be equal to 0, and change T with respect to Y2, and that should be equal to 0. So the physical principle should be, or the physics that's going on should be very clear. We take the derivative, so let's do an explicit calculation. We did this last time also for one thing, but we want to see how multiple points contribute. So this is N1, which is a constant. S1 is this distance here, X1, Y1. Maybe I should also say this is X0, Y0. That stays fixed. Y0 is not being changed, and in the system I'm considering, this is also like at the very end. I want to keep it fixed. Right? I don't want to change that. So this is x1 minus x naught square plus y1 minus y naught square and square root of it. And three legs to that if you want. That's n2 times x2 minus x1 square and again, one should be prepared for generalization. If it was going forever, there will be multiple terms in there. Let's do the first one. Notice that when I'm doing partial derivative with respect to y1, and before that, I should mention that if we were doing the earlier problem, when we were doing only two mediums, we had these two fixed, right? So there were only two mediums, and now we're having three mediums. So where are the places where y1 comes? Important point is that it shows up only in these two. This piece does not have y1. So y1 is in this interface. Even if there were 10 of this, when you're changing with y1, it is only this interface. It cares for only these two, like the adjacent pieces in there. So there's only two pieces that show that. And again, y2 will show up only in these two. If I were to vary y3, it will show in the next three, so only in the two adjacent ones that are. And that's one basic observation one has to make when we are going into a continuous regime. It is one and the next one. So that's the variation part. It's one quantity here and a quantity right next to that. Right? That's the only thing that contributes. It's not that here this changes, even though they are connected, right? That's like the derivative. It's connected to the end point, but as a first principle, as a first variation, it's only the adjacent one that matters. One more point we are saying is that this y1 and y2 are completely independent. Right? When I'm changing y1 and y2, I'm not saying that the amount of y1 I'm changing is related to y2. They're completely independent variations. And that again, we will bring in when there are continuous variations going on. Here, change in y1 here, for example, it can go all the way top. I don't care, but y2 could be arbitrary independently. So there are two independent arbitrary variations. And that again, we will make a statement about that. And that will be the basic principle that will take us into the formal definition of this derivative. Okay, so let's see what's going on here. We want to take the y1 derivative. This is equal to n1 times 2 times, or not 2, right? So this is y1 minus y0 over x1 minus x0 square plus y1 minus x square. And we know that this is y1 minus, so if you were to see this as this over s1, you would say this is angle theta 1. So that's where the Snell's law comes in, sine theta 1, n1 times sine theta 1, and the next angle is n1 times sine theta 2. That plays a role. Here, this is minus, so notice minus is coming from because y1 is having a negative sign here, times n2 times y2 minus y1 over x1, sorry, x2 minus x1 square plus y2 minus y1 square. And that is 0 here. Just to clarify, that's 0. Yes, no contribution from the total. Same thing here, derivative of t with respect to y2. The first term does not have y2, that's 0. And the second one is plus n2 times y2 minus y1 over x1 minus x0, the whole square plus no, it's 2 minus x1 plus y2 minus y1 the whole square minus n3 y3 minus y2 over so that's what if we were to generalize this, and that's your statement in principle, right? You would say I can capture this in a single statement that if I had many of them, so let's say t, so now I'm generalizing this, if t was a function of y1, y2, y3, and so on, I keep going forever. In fact, I could have written this as t of yi. That's where I means that it is 1, 2, 3, so on, right? So where I is equal to 1, 2, 3, so on. And that would have been equal to n summation of I going from 1 to, let's say, n, or it could be infinity. I keep going forever. I don't say where I'm stopping. And this is n I times si. And each of that is this, where this is equal to I going from 1 to either a fixed number n or infinity. That's equal to ni times xi minus xi minus 1 square plus yi minus 1 square. And one can also see what is for what yi is 0. This time I would require that derivative with respect to all i's. So y1, y2, y3, all the derivatives has to be 0, right? So this is equal to 0. So for each I is equal to 1, 2, and so on. Right. So there are many of them here. It's like here there were 2, earlier there was 1, 2, 3, 4, 5, and so on. And the condition here is the same, right? This is n2, for example. I should have said maybe I can say this is nothing but n1 sine theta 1 is equal to n2 sine theta 2. That's your derivative. So here you would say this is n1 sine or ni sine theta I minus so this is I and this is I plus 1. So this is ni plus 1 and sine of theta I plus 1 is equal to 0. Again, for each I is equal to 1, 2, so on. All this should be at least intuitively very clear, right? I mean, we are basically starting with a minimization principle and taking the derivative makes it stationary in the sense that it minimizes it if it was if we interpret it as a velocity derivative is being taken as zero. So at this point, what we want to do, or what our goal is, that we want to extend this discreteness to continuous. We want to make this really a continuous variable. And notice, where is the discreteness in there? It is in this 0, 1, 2, and so on. Or better, it is in this y1, y2, y3, y4, and so on. So our idea would be, let me go here. So our idea is, so t, which was a function y1, y2, so on. And we in fact went ahead and said this is t of, or let me write it here. So this is t of yi. Okay, visible. So this time I want to actually write this as a function, right? So this is y1, so this is continuous. So what captures the continuous part? It is going to be, instead of I, I'm going to write this as y of x. So not this x, the x0, x1, x2. Now I'm going to go continuous here. So x gets the idea of I. It's like saying that if you have a vector ai, where this is a1, a2, a3, that's the idea of a vector, a finite dimensional vector. Let's say, even if there are infinite, it's having discrete components in there. Think of a function now. So this is a of x. This can be imagined in a very hand-waving manner, that this components a1 here is ax. For each x, there is a value of a. So in that sense, a is a function of x, or a is a component of x is the component of a, if you want to think of it in the language of a vector. So this will be the idea of a functional space, function space. Let's say this will be a vector space. And in that spirit, this is a function space. And you can take the ideas of vectors into functions. For example, there is a dot product, there is a, for example, let's say scalar product. This is the basic idea we will take. If you have ai times bi, two vectors, and this means that there is a summation over I. This means a1, b1 plus a2, b2, and so on. And if you want a function now, so there is a of x and b of x. I want to add over all the variables of x, then I would say this is integral. And I can put a limit on the x. So let's say this is a to b, or a and b could be infinity, that infinite now minus infinity and plus infinity, right? So this is a scalar product. That's it. I mean, that's all there is to it, right? This is the connection between. And that's what we want to think of. And in that sense, when you go from here, if you add down here, you immediately see that, oh, instead of the sum, I will write this as an integral. So let me at least write that, and then the minimization problem, we will come back to that. So let's, so now we are saying the same idea, but now we have, let me say, this is a box and that's your X, continuous variable. Refractive index N is a function of X. It could be increasing or decreasing, right? For each value of X, there is a refractive index, no more discrete. It is a function of X. And you would like to actually still go from this point to this point. Instead of going in this breaks, I would go like this. So I can now have a functional, a continuous path going from one point to the other. And in principle, I don't know which one is the right one. So all possible paths, right? So this is an arbitrary path, or this is a random path, right? And we have to minimize this. That is one out of, let me draw many paths so that, so this could be another path. A straight line is also an example, right? Out of all these possible paths, there are infinite of them. Out of all this, there is one which is taking the shortest path. Right? That's what we would like to do, right? So having clarified that, let me do this. I want to show only one path. So let's say this is, I would like to calculate the minimum one. And for that, I know I need to calculate t, right? So the t time taken is equal to sum of all the times. Here it was t1 plus t2 plus t3. And I will have to integrate the time taken for every tiny element. So take a small piece here. That's dt, the amount of time it takes to go from this tiny element ds. So this is ds is dt. So and this is equal, and this is when I say integration, there are some limits going from here to there, but I'll put the limits when I write it in terms of x. Give me a minute for that. dt is nothing but definition of velocity. ds by dt is v, right? So immediately we know that dt is equal to ds over v. And let's put a c there, put a c there. So this is n times dn. So that should be correct. So this is integral of ds times refractive index n. Right? So that should be, that's the same idea as here. We are breaking it into small elements. Whenever I'm doing an integral, it is convenient to use one of the variables that the function is given as, right? I would like to write this in terms of x instead of the arbitrary ds here. So we try to get the distance, right? What is distance? ds here is a tiny element, right? Here, so this is a small triangle there. ds squared is equal to dx squared plus dy squared. So ds is square root of that. If you want, that's a metric. We are saying this is a flat space. If this was on the surface of a sphere, we'll come back and talk about this, say, similar things on the surface of a sphere. Then this slightly changes, right? ds is not rectangular. I would like to write this in terms of dx. So write this as dx times square root of 1 plus dy by dx. So I have t is given as, now it's a limit. I can put a limit, right? So dx times let's say n as a function of x times 1 plus derivative of y with respect to x, the whole square. And now I can put a limit. Let's say this is yeah, let's call this x1, and what should I call it? X0. There it was x0, right? X0. What should I call this? I had no name there. Xn. No, not X. Capital. Not a good notation, but let's survive this. That's your that's your new time. If you expression for time it takes from here to there for an arbitrary part, right? Here y is arbitrary, right? Y, what is this y now? Y is a function of x, correct? So this is y as a function of x. And that is arbitrary at this point. Out of all possible functions, y of x, there is one of them which minimizes this t. Is that clear, that statement? Out of all possible functions y of x, there exists a very special y, there could be more than one maybe. There exists a special y which will minimize this time. Correct. And that's the generalization of going from here discrete to this. And we would like to find a way to do that. Like here, we showed that our derivative with respect to y, but now how do we proceed in this? Any questions at this stage? Is still phrasing the problem. Now we want to have a methodology to get these derivatives done. Okay, so the statement that this is a function of y will be written in the following manner. So this is t, and now notice this is going to be written as a square bracket of y. Notice I have not written x in it. Right? Earlier I wrote t as a function of yi, and then I wrote brackets and y of x. This will be written in this form. So this is the language or actual formal notation. So this is x0, this is xn, dx, just copying except for this. So this one plus d x. If you want, this has a functional x dependence. I'm showing all the explicit x dependence. Notice why I don't write the x. X is integrated upon. After I integrate upon something, the left hand side should not depend on it. Right? After you integrate it, it only depends on x down and xn. So there is no point in showing that x there. I can replace, this is dummy, I can replace x with x prime, and that's perfectly fine. That's why you don't write that. Question? Yeah. So this is called a functional. So t is not a function of y. This is not a variable. Each one of this y is a function, right? So is a functional of y. Like y in the sense it's y of x. So that means to say that I change this function and t changes. T depends on which function we are talking about. And we would like to, of course, minimize that quantity. How would I change this? Now, if I were to make a variation, we would like to now talk about a functional derivative. So if we want to minimize this, we want to talk about functional derivative. That's what we want to cover. A few things. This is a standard notation. It's mostly in advanced theoretical physics. This is used, that's very standard concept. I looked up on the internet, there are stuff, but there is not much very useful information in there, but feel free. I mean, I might not be the best searching, feel free to get your own stuff, but there is one book which I found useful. This is Gelfond, the Russian school, Gelfond and oh, this is the second key. Oh, yeah. Gelfond form. It's a whole book on it, but just the first chapter is what you will need. And I think the first or at the most 2 chapters is all that you need. It's maybe about 50 to 100 page book. So look it up. So that's what I would recommend. I don't think it is available on free, what is this called, archive.org, but it's up to you. But for our course, whatever I'm teaching you, that should be sufficient. But if you want to explore more, then that's what do. Okay, so how do we go about doing this? So let's go back to the very basic, like let's get the derivative, like basic derivative, right? So basic derivative or one variable derivative. Right? This is the first thing you're going to learn in a calculus course. It's too elementary for this course, but let's do this. Let's say if you have a derivative, f is a function of x. And let's also have a specific example. Let's say f is sine of x. We know the derivative is cosine of x. Actually, let's take a simple one. X squared or x cubed. X squared. How do we define derivative? The basic idea is that I make a small change in x. So let's have x here. I plot f. This could be an arbitrary function. At some point, x, this is my value of the function at that point, so that's your f of x. And our idea is that I want to make a small change in x, so x plus delta x. So let's say I go to x plus delta x. Or let's say x plus delta x. Make a small change and then take the limit delta x going to 0. Right? When I do that small change, in general, f will also change. And here, this will be f of x plus delta x. And the derivative is the idea that if you take this limit delta x tends to 0, what happens to this slope? This was the idea of velocity, historically speaking. First time when we were defining velocity, it was Newton who wanted to do this. And there was a lot of confusion there in literature as to what happens if you take the limit. Like you would like to define instantaneous velocity, not dependent on 2 points, on a single point. And it seems like this will be a 0 over a 0, right? So this will become 0, and this will become 0 in the limit. And it leads to the idea of 0 over 0. That's not well defined, right? Especially in the early times of calculus. So there was a lot of hesitance in identifying that, and one had to come up with a concrete idea of limit, right? So you say that it is limit in the limiting sense, sometimes, not always, like sometimes, limit delta x tends to 0 is well defined. There could be situations where this is not that's delta x. So let's see how this works out for x squared. Right? Let's actually take this limit and go over this a little bit and see what are the features that comes in. Is this really an approximate quantity, or is this exact? Are we neglecting something when we are taking a derivative, or so on? Okay, so this is equal. So let me now switch to this example, right? So I'm saying limit delta x tends to 0. Now this is x plus delta x squared minus x squared over delta x. Again, notice in this limit, it seems like there is a 0 in the denominator, right? Which is never, one has to be very careful with that. If you expand this out, delta x tends to 0. This is x squared plus 2 times x delta x, and then there is a delta x squared minus x squared. Notice the first term, actually, let me write this again. Right? Limit delta x tends to 0 is, this is x squared over delta x plus 2x, right? Delta x cancels out, plus delta x minus x squared over delta x. And here, in this way of writing it, you see the subtlety. This is infinity, right? If I were to take the limit first, right? First, if I take the limit and then do the subtraction, you're actually subtracting two infinite quantities, which is not necessarily 0. But you say that no. First, I have to subtract and then take the limit, right? That's the idea of derivative. But this is subtle, right? This you're subtracting, and similar thing you're going to bring in here. And what about this? Like, what happens to this? This seems to be the answer, right? So this cancels out. Okay, I can agree if you do the order correctly. First subtract and then take the limit. That goes away. What about this? Right? And one would say that is that an approximation, or that's small comparing the small delta x is small, but that really goes to 0. Right? That always goes to 0, and that's your answer, right? 2 times x. So there are two features that always happens in this kind of approach. The first term, which is actually f of x, will always cancel out. So this cancellation, which is basically in a sense infinities, they always cancel out in this derivative descriptor. And there will be terms which will go to 0 in the limit delta x goes to 0. There will be many of them that goes to 0. Because it was x squared, there was only one term. Think of sine of x. Sine of x will be a whole series, and there will be a whole set of terms that will go away in the limit. So many terms go to 0 exactly, it's not an approximation. They exactly go to 0. And whatever remains is your derivative. So those features you want to capture or have in your mind. And let's now go and try to do very similar thing here, but maybe do a little bit of warm-up mode. So this was a one variable derivative. Now let me do a discrete variable derivative. Right here, there is discrete variables. So this is one variable, then we'll do discrete variables, and then I'll come back and do this functional derivative on its own. Okay, so maybe keep this here. So let's have let's have a simple for discrete quantities. Let me have f y I is a vector. So this I will write as vector y. So the y I components of a vector will be y. Let me have a function f which is equal to y dotted with a. So that's a simple dot product. More explicitly, I don't say it is in 3 dimensions. So this is y1 a1 plus y2 a2 and so on. That's what it means. Let me define a gradient operator that's equal to d by d y1 and d by dy2 and so on. It is rectangular coordinate, it's I hat, j hat, so. And now I want to define what is gradient of f. I want to define gradient of f, and we would say that this is equal to gradient of y dotted. This is gradient with respect to y, right? So be careful. Usually, our temptation is to always think in terms of x. So this is instead of x hat, this is y, right? This is with respect to y1, y2, y3, not x1, x2, y2. Right? So be careful with that. So that's dotted with a. That should be something you have seen in electrodynamics. That's where you get this gradient operators a lot. But anywhere, it doesn't have to be electrodynamics. Anywhere you see a gradient of this, what is this equal to? One can write the answer immediately, but then I want to go through it carefully. What is this equal to? Let me start with that answer and then we'll. Is this a vector, scalar, answer? It should be vector, right? There's a vector on the left, so it has to be a vector. So what is that? Yeah, very good. If it helps, yeah, a is a constant. A does not depend on y. A does not depend on y. In principle, it can.
I think it's A1, A2, A2.
Good. So the components, that's very good. So that's A's, right? A1, A2, A3, that's just vector A. Right. Very good. Right. So how do you see this? Right? So let's go through this a little carefully. So let's say this is the I mean, maybe we can use index. Let's say this is del I. This means that ith component, right? So that could be one way of seeing it. So that's f, that's equal to gradient ith component of the gradient. And this is y dotted with a, and let me write that just as y dotted with a. Dot product can be written in terms of indices. That's just a sum, right? So this is I, y. I cannot use I because I shouldn't be using the same thing again, right? So this is j and aj. And what does mean? There's a small summation notation here. summation notation is that if the index repeats means it is summed over. Is that familiar? Abdullah? Is that a familiar thing? Summation notation, index notation?
I heard about it, I don't remember.
Okay, that's fine. Yeah. So what I mean here is that JJ, so there is, one should read this as a summation over J. Okay. But that's one way of saying it is that that's too much clutter, right? I don't want to write so much. I want to be lazy. So you say that, oh, I'm going to ignore this, but then I don't have the information about that sum. But then you say that because J is repeated, J comes twice. Anything that comes twice will be thought of as summed over. Is that familiar, Arvind?
Yeah.
You seem to be, right? Okay. And others, I think I've seen it in my course earlier, so they have an advantage. So we won't, how much will we use? We'll see. Yeah. Okay. If necessary, I'll go over it again. Okay. So that's this quantity. A is a constant, I said. So this gradient acts only on this, right? So we are saying this is partial derivative. So this is del I yj. I can use a parenthesis to clarify that this does not act on A. A is a constant, right? Aj. And that asks the question, what is this quantity equal to? So we need to know what this is. So there are different ways of writing this. So I can either write this down from here. Notice I should emphasize that there is no operation in between. These are two vectors. Usually when we have two vectors, either we take a dot product or a cross product, right? This is having nothing in it. That means this is a tensor. Often you write this as cross. And that means it is the outer product of two vectors. I will not write that. I find it's the dyadic notation where you don't write anything. It's called dyadic notation. It's a 100-year-old notation. Right? So this is a tensor in a sense. This is also a vector. That's also a vector. So a two vector sign. This is a, if I were to use indices here, that's the same as del I, let's say downstairs, del I yj. And let me be a little sloppy. I'm using double notation here. That's it. This is equal. So the components of this tensor are this. That's the correct way of. What is that equal to? That's partial derivative of yi with respect to yj. There are a lot of combinations here. Let me write that explicitly. J can be 1, 2, 3. I can be 1, 2, 3, or for that matter, plenty of them, right? So let me write this as dy1 over dy1. So this is dy2 over dy1. And let me stick to 3 over y1 or and keep going, and there is more of it, right? So this is dy1 over dy2 and dy2 over dy2. And so on. And I can keep going on this side also. So there's a bunch of them here. So I can collect them as a matrix if you want. These things, there is so many of them. And now you ask, what is the variation of y2 with respect to y1? Notice here, when we were making a variation, I changed y1 and I changed y2. Like those are exactly the two y's that we are saying. And we are asking, what is the change in y1 when I make a change in y2? And we agreed upon right in the beginning that these two variations are going to be independent. This change should not affect that. Right? That was our assumption to begin with, that these are independent variations. And that independent variation requires that change in y2 with respect to y1 is 0. Like these are independent variations, right? So all this is 0. This is 0, all of them 0. This is 0, that's 0. That's a requirement of the problem, right? We are talking about a situation where all these variations in each component is independent of each other. And what is dy1 over y1? What is the variation in y1 due to y1 itself? That's 1. Right? So this is our 1. Right? So in principle, this is equal to 1, 0, 0, so on. So this is 0, 1, 0, 0, 0, 1, and so on. The whole matrix is purely diagonal. That means to say that this is equal to Kronecker delta ij. Is that a familiar idea, Aryan and Abdullah? Right. This is equal to, so this is a notation, which means that this is a notation for this, if you want. Like that's an identity matrix. If I is equal to j, so count this as I equal to 1, I equal to 2, I equal to 3, that's the name of the column, and this is the row. This is equal to 1 if I is equal to j. If row and column are the same, then it is 1. If they are not the same, that's equal to 0. That's a notation for that, but this is called the Kronecker delta. So what we have done is we have shown is that this gradient of this y is delta ij, which is basically a Kronecker delta. We will also use, if we are in this notation, we will say this is 1. There are 2 vectors. These are the 2 vectors. Right? That's 1 means that this is a tensor. Right? That just exactly means del ij. Like in the dyadic notation, this is this. If you go back here, like you guys gave me the right answer that this is A, but now you know how this comes about. This is equal to 1 dotted with A. And 1 times A is identity times the vector is the vector itself. Or if I had to do this here, right, you would say this is delta ij times aj. This is delta ij times aj. And then you say that, oh, this survives only when I is equal to j. So as well, this is a. So there's a good bit of index notation. I used orals. This is the dyadic notation. Either way, you want to convince yourself that this involves this in here. Now, this one of the simplest functional derivative I can define is, instead of saying y dotted with a, I just create an integral. I make this continuous. So let me do a simple example at this point. So, and we'll come back to this example next time. Yeah, let's see, where is this? Okay. So we want to go parallel to this. Let's have a functional of y. That's the equivalent of saying this is f as a function of y. Now this is, instead of a dot product, I integrate, right? So this is y of x A of x, and this is df integral dx. Let's say this is from A to B. Like, is the analogy clear? So this is dot product y1 a1 y2 a2 so on. This is an integral at this point. That's the analogy in there. And I want to now take a derivative with respect to every point in y. Right? So the gradient now will be, so the extension of this gradient will be, I want to make this small, so I want to change f with respect to every point in y, which is, let's say, y of x. So let's call this x prime. This is an integral in that x prime, so that I keep this as a free variable. This is the extension, or by analogy, that's your gradient. So gradient, remember, was d by dy, right? So instead of yi, I change it to x, right? And this is a standard notation. Instead of writing partial derivative, you write delta for functional derivatives. So if I want to make a change of this with respect to y, or sorry, the function of f, so I want to do this, f as a function of y. That's what I'm interested in, right? So this is the equivalent of writing gradient of this function f. This will be the same as y of x of the x prime a to b y of x prime a of x prime. This is a quantity dependent on x. That's something x prime, right? So I can go through that integral, and that involves a to b the x prime, and notice what I'm writing. This is a change in y at x prime with respect to a change in y at x, and that's a of x prime. This quantity here, we want to be, let me define this. This is going to be, let me first write it. This is change or variation, right? That's oh, I didn't move it then. So variation in y at, variation in y at x due to variation in y at x prime. The same idea here. This was a variation in y at 2 due to variation at y due to 1. And we said that this is 0 unless they are the same point. So it has to be 0 or 1. But now this is a continuous function. When I add up all these things, there should be a constraint that I should get the area of the function. And that's not possible unless you define a delta function. So instead of delta ij, the Kronecker delta, I will require this to be a delta function. This will be x minus x prime. I will talk about more on that here. Is a delta function familiar? Aryan and Abdullah?
Yeah.
Right, delta function, we'll talk about this a little bit, very practical something.
That's a variation in y at x prime or x.
At x prime, right? Oh, here, a variation in y at, yeah, so maybe x prime due to x. That's what, yeah, I should have reversed it here. variation in y at x prime due to variation in y at x. Good. Thanks. And this I say is 0 all the time. It is 0 every time, except when x is equal to x prime, which technically should be 1 if it was discrete. But then there is this, if you're doing a continuous thing, you have to add up to give you a 1. So that requires that they should be infinite. And we'll come back to that. I can convince you on that next time. But at this point, it is delta function, not really 1. Or yeah, we need a quiz, right? So why is it infinity? Why is it not 1? Delta function is x at x equal to x prime. Why is it not 1? Like with the analogy of Kronecker delta, you would have said this is 1 at x equal to x prime and 0 otherwise. Why is it not 1? Instead, you say it is infinite. Right? So what happens if it is 1? Right, so think on that. But for the keeping the time limited, so let's go and solve this. So the first functional derivative we are going to do now. If we assume this, go back, right? So the functional derivative f, the first functional derivative we are doing with respect to y of x is equal to a to b of bx prime of, now I can say this is x minus x prime of a of x prime. Right? What's that integral? Equal to the delta function integral. A, right? So what you do is whenever you have a delta function, look at the argument, set it to 0, so x equal to x prime. So forget the integral, replace everything at x prime. So this is a of x. That assumes that this delta function survives within a and b. So there's that additional condition that let's say that's a of x. And that's your very analogous to this, right? You got a vector a. Exact same thing. That's the basic idea, and we will now exploit this more. And we'll come back and clarify. Any comments, questions? And I'll post the homework in the next few hours, so that basically homework will be given this, take a functional derivative, a lot of functional derivatives, maybe about 10 or 20 of them. It's like a normal math course, right? You practice a lot. And then we will come up with physical problems later. The next homework will be physical. That's all. Thank you.